So to answer any of these questions on deducing the allowed quantum numbers of an atomic electron, you have to know the rules for quantum numbers. So n is the principal quantum number, and n basically represents the energy level of the shell, if you like. So that is the energy. And it can take integer values from 1 onwards, okay? And then L is the angular momentum quantum number, sometimes called the azimuthal quantum number. And that represents the shape of the orbitals. Okay, so remember, it's a probability distribution function. So there's like a 3D boundary surface for each of those, what you would probably refer to as a subshell. Okay, so that can take all integer values from 0 up to n minus 1. So L can take integer values from 0 up to n minus 1. So you have to know what n is to work out the allowable states of L. And finally, M subscript L is the magnetic quantum number. And what that tells you is if there is more than one orbital for a particular subshell, like how many of them there are, or the multiplicity if you're going to be fancy. And that will take integer values from minus L to plus L. Okay, so it basically tells you the orientation in three-dimensional space of those of the different orbitals that there may be. So that can take integer values, including 0, from minus L to plus L. Okay, so again, you have to know what L is in order to define the possible values for ML. Okay, so the principal quantum number. So the principal quantum number is analogous to what you've probably referred to before as a shell, and the angular momentum quantum number is what you've probably called a subshell before. And in fact, the notation NL is what we call subshell notation, okay, which tells you what subshell an electron is. And then the magnetic quantum number M subscript L is the individual orbital that an electron is in. Okay, so now to answer this question, then what is the smallest possible value of the principal quantum number n for a d electron? So you also need to know the letter designations for the numerical values of L. So L can be 0, 1, 2, 3. It even goes beyond 3, but you won't commonly encounter them for any electron in a ground state atom. So 0 corresponds to an S, 1 is P, 2 is D, and 3 is F, okay? So when we're talking about a D electron, we're talking about an electron that has L equals 2. So if L equals 2, is asking what the smallest possible value of N could possibly be. Well, L equals 2 can only exist if N equals 3. Because the highest possible value of L is at n minus 1, okay? So if n minus 1 equals 2, therefore n must equal 3. So that is the smallest possible number of n for L equals 2. You could also have larger values of n, like n equals 4, n equals 5, but you can't have n equals 2. There's no such thing as a 2d electron or a 1d electron, if that makes more sense. If you still don't believe me, it's a really good idea to actually go through your possible values of n and the corresponding values of L and ML. So for n equals 1, the only possible value of L is 0, okay? So if L is 0, the only possible value of ML is also 0. What does that correspond to? That corresponds to the 1s subshell. And there's only one of them because there's only one value of ML, okay? For n equals 2, well, you can have L equals 0 And because L can take values up to n minus 1, well, 2 minus 1 is 1. So you can also have an L equals 1 state. So if we stick with the L equals 0 for a second, if n equals 2 and L equals 0, the only possible value for ML is also 0. So that would be your 2s subshell, okay? For L equals 1, ML now has 3 possible values, minus 1, 0, and plus 1. So there's 3 possible orbitals for an L equals 1 subshell. So the NL subshell label would be 2p. So there's 3 2p orbitals. So for n equals 3, now the maximum value of L is going to be 2, because remember the maximum value for L is n minus 1. So L equals 0, L equals 1, and we now have the possibility of L equals 2. Okay, so for L equals 0, that only allowable value of ML is 0, so that would be my 3s orbital. For L equals 1, ML can go between minus 1, 0, and plus 1, so there's 3 possible values of ML, okay, which is telling me there is 3 2p orbitals. 3p orbitals. So it's 3 times the 3p orbital. Then for L equals 2, the possible values of ML range from minus 2 to plus 2, including 0. So that's minus 2, minus 1, 0, plus 1, plus 2. So there are 5 possible orbitals, and the subshell designation is n equals 3, L equals 2 would be 3d. So there are 5 3d orbitals. All right.